Welcome everybody to the mastery review. Glad to have I have 17 people. I'm happy about that. So the mastery starts actually in an hour, and this is just a chance to go over questions. I have up on my screen already the derivatives practice sheet that I sent around a few days ago. I can work some problems off of that, or if you have some that you want to see, I can do that. Does anybody want to start us off? You can put it in the chat or, all right, let's see. I was hoping you could review derivatives with natural logs. All right, let's do that. So I'm gonna pull a few from the sheet that I sent around. So here's the sheet that I sent around. Let's pull a couple off here. Let's look at 17 and 18. So y is ln 2x, and then y is ln x cubed plus 5. And then let me scroll down and do it. Let's get a couple more complicated looking ones. Sorry about that. It skips around. So let's look at number 42. That looks like a fun one. The function is ln e to the 2x times sine 3x and all over rad x. And there was one more I wanted to look at. Let me pull that one. I'm going to pull one at the very end here, number 63. So I'm going to copy that one down. And I'll work these four. The first couple won't take long at all. All right. So I'm looking at I have four copied down. I'm going to go to my overhead here. Ready? So the general rule, let's put it over here. Y is ln u. Then the derivative is going to be du over u, where the du represents the chain rule. So you basically just plop you put the what's called the argument into the denominator and then its derivative on top. And in this first case, we just go ahead and put 2x on the bottom, and then I'll put the derivative on top. Well, the 2's cancel, so you just get 1 over x. Yes, in that practice sheet, there are some with hints saying do certain things. All right, so the question is, how do you know? Well, you just kind of practice and you determine which method is the best. I'll discuss that as I work through these. So let's look at the second one here. You want to, in this case, I'm going to use a log property here. I'm not going to take the derivative yet. The square root is the 1/2 power. And then I'm going to use the power property of logarithms where the 1/2 actually comes out in front. Now, this is not a derivative. This is actually a property of logarithms. Now I'll take the derivative. So the 1/2 now is in front. Put the argument x cubed plus 5 in the bottom. Put its derivative on top. You are done. Okay. So one of the nice things about logarithms is that they have these three properties, and maybe I can stick them here on the right. The log of a product is the sum of the logs. So you can break apart a product with the addition. The log of a quotient is the difference of the logs. And then the log of a power is where you just bring the power down in front. It looks like the power rule for differentiation, but it's not. It's actually just a property of logarithms. These are actually the identical properties of exponents. Logarithms are exponents. And because of the natural logarithm, there's some nice mathematical properties of the natural logarithm. We tend to use the ln almost exclusively once you get into higher mathematics. All right, so now, okay, now you get a problem like this. This thing looks like a nightmare. And you might be thinking, oh gosh, I have to put this in the denominator and then take its derivative in the numerator. Well, you're going to be doing this problem all night if you try to do it the direct way. So this is definitely a case where you want to break it apart using the properties. So we're going to use these three properties here to break it apart. So at the multiplication symbol, I'll break that apart as a plus. And then at this division symbol, I'll use this property here, break it apart as a minus. Okay, so again, I haven't yet taken the derivative. I'm still working out the I'm basically simplifying it using logarithms. Now ln and e cancel each other out, so all you have here is 2x. This one is still just kind of waiting for you to simplify for now. And then here I'll do the same thing I did a moment ago. I'll bring it's actually the 1/2 power. I'll pull that out in front. Okay. Now I remind you once more, this is not yet the derivative. This is still the original function. But now we're in a position here to take the derivative, and it's going to be a lot easier. The derivative of 2x is just 2. Derivative of ln sine 3x, well, just use the property, put sine 3x in the bottom, put its derivative on top. Notice there's an extra chain rule step with that 3, so we'll put that out there. Then here, the 1/2 just is a coefficient, and it's just ln x, which is 1 over x. And believe it or not, we're done. So about 90% of the work was done with the simplification. And I'll pause here for a moment. I want to do this last one here in a second, but I'll pause here for a moment. If anybody has any questions on what I did, I'd be happy to discuss. You can put it in the chat or just simply, verbally come on in. Anybody, does this make sense what I did there? Okay. All right. Again, you can always ask. I can always go back. All right. So I want to point out an obvious difference here. This function already had an ln.
But I see.
Somebody's audio.
Could we go?
Yeah, go ahead.
Really quick, can we go over how we got 3 cosine 3x on the second part?
That's the derivative of sine 3x. The numerator in the logarithm derivative is the chain rule. So
okay,
we put the sine 3x in the denominator and then its derivative in the numerator. Are we going to use Scratch for the exam? Yes, you are. You're just not going to turn it in. That was, I mistyped that or misrepresented it in my email. I've been dealing with that fire now for almost a week. Okay. This problem here, so let's take a look at the obvious difference. This problem already has an ln in front. So you get this nightmare function here, but the ln will allow us to break it apart. This thing doesn't have an ln in front. So yeah, without using logs, could you apply the quotient rule? Yeah, you could, but you'd be doing this for like 15 or 20 minutes. I mean, I encourage you, give it a try. And I think after about 5 minutes on it, you're probably going to say, maybe this logarithm idea is a good idea. I would not want to mess around with trying to do the quotient on this one because then you have nested product rules and then you have nested chain rules. This thing's going to just spread out over 2 pages. So this one, it lacks an ln. It would be really nice if there was a natural log here because then I could use the properties to break it up. So what I'm going to do is I'm going to go ahead and put one in, but I have to do it on both sides. So give me a moment to write. Yeah.
It's kind of hard to see that X9. What's the symbol that's right
It's
next
a
to it?
90.
90. Okay.
Yeah. All right, so this is the function. I just popped in some ln's on both sides. Question was, we're not required to simplify further as long as we get the derivative. Yeah, that's fine. You you can leave it. Take care of some obvious ones, but that's even optional. All right, so let's come over here and take the derivative. We're going to do this actually implicitly. On the left side, it's 1 over y, and then its chain rule will be dy dx. On the right side, well, actually, you know what? I apologize. I kind of jumped the gun here. Let's break apart the expression here on the right side, then we'll worry about derivatives. So again, I'm going to use the same properties I have up here. I'm going to break apart any multiplication as a plus, any quotient as a minus, and any power by bringing it out in front. So this multiplication here becomes a plus, so it's going to be ln x to the 90 plus ln tan 7x. Now this quotient then becomes a minus. This becomes ln e to the 3x. Now right here, I have to be careful. That's actually a multiplication right here between them. I'll put a parenthesis because I'm actually minusing off the whole denominator. Now, what'll happen here in a moment is this minus will actually distribute and make this plus a minus also. But for now, I'll leave it the way I wrote it. Okay. Now that looks like a lot of work, but you know what? We're actually about 75% done with the problem. Let's go ahead and continue to use our properties to clean this up a little bit. Bring down any powers. The couple middle terms don't have any powers. Actually, right here, the ln and e cancel, so we just get negative 3x. This minus now moves through, and oh, you know what? I left off the ln. Oop, let me put that back in there. All right. So right now, how did the ln cancel? ln and e, they're by definition opposite operations. Natural logarithm is the logarithm of base e, where base e raises something to an exponent, natural log brings the exponent down. Another way to look about it is ln of e is 1. So e to the first power is e. Oh, I'm sorry, e to the first power. Yeah, that's right. E to the first power is e. So if the 3x comes out in front, there's actually a hidden 1 right there that we don't need to write. Okay. Now I'll take the derivatives. So this becomes 90 times 1 over x. This one is tan of 7x in the bottom. So then a derivative of tangent, and that's a good question to know. That's secant squared of 7x. And then there's a chain rule with that 7x, the 7. All right, put it out in front. Derivative of minus 3x is just minus 3. And then let's come over here. We have ln sine x. So we put sine x in the bottom. And its derivative cos x on the top. And now we're almost done. Secant squared, that's the derivative of tan x. So that's a form you need to know. And then one last step is to bring this y up. Now I'm going to multiply both sides by y. I'm actually going to move this y in front of all of this stuff. In fact, what I'm going to do is I'm going to copy all of this stuff. Let me just give me a second here. All right. So all of this stuff here just gets copied here. I'm leaving some space right here. This would be where y goes. Okay, does the ln just disappear for ln sine? No, I'm taking the derivatives. That's kind of the whole point. Once I've got the natural logarithms spread out and simplified, now I differentiate. So right here, this is the differentiation line. Okay, this is where I'm actually performing the derivatives. Okay, and then again, the property for logarithms is du over u. So just take the argument within the ln, put it in the denominator, put its derivative in the numerator. So the last step here where I bring the y up. Well, y originally was this function here, so I just copy the function back in place. So I just literally just copy the original, place it back, and we are done. Now this thing, yeah, this would be about the worst possible function you'd ever see if you try to take its derivative. But natural logarithms make it so much nicer. You know, look how I was able to do it in about 1/3 of a page. If you tried to do this I guess you could say the long way, you'd probably be, again, probably about a 15 or 20-minute problem, and it would look awful. You okay, there was a question here for the exam. Actually, hold on, let me scroll up here. There's no calculator, but there are some questions with negative 0.025 exponents and other that have decimal. That's fine, just subtract one. You can subtract one from those mentally. It's like negative 0.025, you have to take that down and put it out in front. There's negative 1 point, the new exponent would be negative 1.025. So you can still do the subtraction. And if you get a weird thing like x to the pi, well then just bring pi down, x to the pi minus 1. Just write it out as pi minus 1. Derivative of ln is 1 over x times, or x being sine x, then you multiply. Yes, exactly. That's exactly correct. So the comment in the chat was that the derivative of ln, where you just, you basically put the argument in the denominator, that being sine x, and they put its derivative in the numerator. Alrighty.
Question really quick before you
Yeah.
move on. When you put that equation, the original equation in front of what we found for the derivative for that, yeah. Typically for the chain rule, it's the derivative of the outside function, and then you do the derivative of the inside function multiplied afterward. Where
Right.
is that formula coming from? Like the original equation?
Not sure the following. This is really just more of a procedural step because I'm actually using implicit form right here. It's kind of a trivial implicit, but the function y is temporarily caught up inside a natural logarithm. So I follow the logarithm rule, which is 1 over y times its derivative, which for now I'm just writing dy dx.
And it's coming, that original formula is coming from that implicit differentiation.
Yes.
Oh, okay, I understand now.
Okay. Now,
Yeah.
algebraically, I want to solve for dy dx. So that just means to multiply both sides by y, but literally just bring the y up to here. So this whole expression here gets placed into just a big bracket.
Yeah,
I didn't
that
make any
makes total
changes.
sense now.
And then just pop the function back in. Believe it or not, I mean, again, this would be what you got if you work it out the long way. It would probably look ugly, but that would be what you got. Also, believe it or not, this is simplified. So that's one of the beauties of using logarithms is that it does a lot of the simplification for you as you go along. I find that to be really nice. All right, so that was a good discussion on logs. Any last questions on these ones? All righty. Anybody want to suggest another question?
It's complicated for
No,
you.
that's all right. So the function is arctan. Sorry, what was it?
2 over x cubed.
Over x cubed.
Yep.
All right, and then there's so Dylan asked for number 58. We'll get to that one. And then arcs, arc sine. Yeah, I'll discuss the arcs with you here. So there's two arc trig formulas you should really know. The main ones are the arc sine. I'll put the forms here. I'll tell you what, I'll use that dx to represent chain rule. And then the arctan, that's the other common one. In fact, the arctan is extremely common when you get higher up. In Calc 2, you use it a lot. It's actually a really common form for integration too. The arc cosine is just really the same as the arc sine, but with a negative in front. So that's why we just kind of opt for arc sine. All right, so let's do the arctan. So I'm going to follow the form here. And I'll just write it out. It's kind of look ugly at first. So I just put the 2 over x cubed inside this bracket here. So I'm following the general form for the arctan that you see over here. And then I have to take a chain rule of 2 over x cubed and put that here. And the way I'm going to do that is I'm going to use the power rule. I'll temporarily write it as 2x to the negative 3. Do the power rule, negative, that'd be negative 6 x to the negative 4. Okay. Now that looks awful, but it is correct. And you know what? I'll bet you the system would probably accept it if you. Let me. What am I doing here? Oh, you know what? So this is actually a correct form. In fact, it's simplified. It's just not very attractive. I'll do a couple steps here just to kind of clean it up a tiny bit. 2 squared is 4. X cubed squared is x to the 6. This, meanwhile, is just actually negative 6 over x to the 4. I personally don't like negative exponents if I can get rid of them. Now here, I'll just multiply through by the fraction denominator to get, if I multiply top and bottom by x to the 6, it starts to clean up a little bit. So then if I bring it together, the x to the 4 and x to the 6 cancel, make x squared. I have negative 6x squared on the top, x to the 6 plus 4 on the bottom. That's the cleaned up form. But, you know, I want to stress that this form here is considered correct. It's just sloppy looking. Does that help you?
Yes, it does. Thank you.
Okay, and then the arc sine, I'll make up an arc sine for you guys. Let's do an arc sine one. I'll just make one up. How about arc sine of throw a curveball at you? How about cube root x? Okay. There's just an opportunity to get some more exposure to these forms. So I follow the arc sine form, which is right here. And I'll just be 1 over radical 1 minus and then cube root x quantity squared, and then the derivative of cube root x. So I treat that as a power x to the 1/3. And I just do the derivative, it'd be 1/3 x to the negative 2/3. And then again, like I just did a few minutes ago, clean it up a little bit. Let's see. The radical, it'd be 1 minus, that'd be x to the 2/3 power. And then on top, this 3 right here actually can sit out in front. In fact, you know what? I'm going to just write it again. Check this out. Because everything actually falls into the bottom. That would be the cleaned up form. Okay. So these are 2/3 powers. But you know, if you get to here, as long as you type it in correctly, as long as your syntax is correct, you've got the parentheses in place, it should be accepted. So I encourage students, you all, to get into the habit of trying to simplify and clean up your answers, because I think you discover that as you use these, it's easier to use these functions when they've been simplified or cleaned up a little bit versus when they're written out in these kind of rough looking forms. If you're going on in math, Calc 2, differential equations, Calc 3, you're going to see a lot of this pop up, a lot of these junky things that just happen, and you're going to be obliged to work with them. So get in the habit of now of trying to make them look pretty. Trust me, you won't go insane so fast. All right, so there we go. We have a couple questions there on the arc functions, arc sine and arc tan. So I'm going to share the screen. Number 58. The function is K of x equals 7 to the x squared plus 1. Yay. And by the way, you know what? While I've got that up here, why don't I take a look at a couple of these? Why don't oh, I didn't mean to do that. Why don't I pull off a couple of these just to kind of discuss them? Because we build up. So for instance, I'll pull off 4 to the x and 10 to the t. I'll write them down here. Give me a second. All right. And then that'll help us work out the third one. All right. Whenever you have a constant base and a variable exponent, these are called exponentials. All right. These do not follow the power rule. The power rule is when you have a variable base and a constant power. If I had x to the 4, I would use the power rule. If I have 4 to the x, this is an entirely different beast. All right. The general form for the exponential. So the general exponential form, if you have y equals a to the x, the derivative is going to be copy the function, multiply by natural log a, and multiply by the derivative of whatever the exponent is. So there's a chain rule. Okay. So for instance, the derivative for y to the 4x is just 4 to the x times natural log 4. And then actually we're done because the derivative of x is 1. And we're done. Okay. The derivative of 10 to the t would be the same thing. You copy it, and then you write ln 10. So that's an automatic maneuver. And then same thing. The derivative of t is 1, and I don't need to write it, so I'm done. So that's the general form for exponentials, that being a numerical base with a variable exponent. So I'll come up to this function up here. So you copy it, you append it with the natural log of the base. Now this one does have a chain rule. The derivative of x squared plus 1 is 2x. And we're done. This one really is simplified. There's not much else we can do to it. And that would be what you type in. Actually, if you were to type this in on your screen, you want to be careful with your syntax. You probably type it in this way. And then you want to, I guess, hit that multiplication. ln, I usually use parentheses. And then it should accept 2x in that form. I would be a little careful typing in the parentheses. Make sure it understands what you mean. And now, as a kind of a general comment here, one of the reasons that we don't use numerical bases, one of the reasons we tend to use e as our base almost exclusively when it comes to exponentials is because the natural log of e is 1. And so that's a nice thing. When you have e to a power, you don't have to write the ln e part because that's just 1. And that's one of the reasons why we like e. E has got some nice properties there. If I had y equals e to the, I'll just make up something. How about x cubed plus 5x plus 2? All right, the derivative of that is just simply to copy it. Then chain rule, 3x squared plus 5. Make sure you include parentheses and you're done. I don't have to do that intermediate ln e part. So that's one of the reasons we like that. As you get higher in math, you probably won't be seeing too many functions with base 4 and base 10 and base 7. Almost always, if it's a numerical base, it's base e, because you can take any other base and convert it to base e. 4 by definition is e to the ln 4, so that just converts it to base e. Just like the previous test, we have 1 retempt. Yeah, it'll be the same format. So yeah, it's just you won't be using a calculator and you won't be turning in your scratch. But otherwise, it's 20 questions, 20 derivatives. That's all it is. It's real exciting. No word problems, and no real numerical calculations at all.
On the ln7 times the 2x on your finish now on this the last one right above, can you also write that as 2x ln7?
Yeah, of course. As long as you're careful with your syntax. So this form is, you want to make sure that the computer understands this, because computers, ironically, are dumb, aren't they? They do exactly what you tell them to do, no more and no less. So
Yeah.
you want to make sure that you enter this correctly. You'll notice I put parentheses around the 7. That's just me being safe. ln parentheses 7. So that way the computer knows that the ln only attaches to the 7, not to the 2x. You want to be careful again with the syntax. All right. So we've got a comment here in the chat. It says, I think with ln and trig functions, they really want the value to be quantized. Yeah. Yeah, and again, these questions are taken from your homework. These 20 questions, if you've done all your homework, they're gonna look awful familiar to you. So I'm hoping, that having that familiarity now, it's almost like the mastery is a final exam on derivatives only. That's a good way to look at it. So at this point, we're just making sure you know your derivatives. And it's a good opportunity to really get some good score and make some good headway in this class.
On the sheet you sent out, I noticed there weren't any problems taking the derivative of a function that had a log base of another number.
Right.
Is
I'm not that will not be on the mastery.
Okay.
And the reason for that is that as you move on higher in mathematics, those functions you almost never see them.
I was a little concerned because I remember it's really weird to enter it into Edfinity. You can't put it in, you have to put like log base of or ln of 2 over ln of x, I think maybe to enter it or something.
Yeah, in fact, if you want, I could maybe do one with you guys.
If it's not on there, it's fine. I just noticed
Right.
it wasn't on there.
Well, that's one of the reasons that we just don't use other bases, because every base can be written in base E. The form is, if you have log base A of x, the form is 1 over x and then ln A, like that. And then, of course, you have your dx if there's a chain rule. And that just looks awkward. And so, yeah, that's not going to be on the mastery. You're probably not going to see it in Calc 2. You're probably not going to see it in Calc 3. I teach Calc 3. I do it both online and in person. And we just don't see those forms. They just don't pop up. We do see a lot of arctans. Be ready. Arctan is popular. All right, so we have a question here. Can you do 49, 52, and 53? Yeah, let me bring it up. I think we did 49, didn't we? No, I didn't. I did not. All right, let me bring it up. So let me share my screen. So 49, 52, and 53. Let me copy real quick. 49 is x sine y plus 2 cos y equals y. We want to find derivative, so we'll use the implicit form. 52 and 53. All right, I'll tell you what. I'm going to copy 52 down. 53 is very similar. It's red, 6 plus 7x on the top. Then e to the 5x on the bottom. All right, let me go back now. So yeah, let's discuss implicit forms. That's a good one to know. So in the first case here, you have x and sine y are caught up in a product, so we have to use the product rule. So it's going to be first derivative, second. Remember, there's the chain rule involved, so dy dx follows, plus the second times derivative first, which is 1. So I don't need to write that. Here, I do derivative of 2 cos y. That's going to be negative 2 sine y times dy dx, again, chain rule is involved, equals, and then the derivative of y is dy dx. You'll notice I have 3 dy dx's to solve for. So what I'll do, tell you what, looks like if I leave this sine y, because this sine y right here is just by itself, I'll leave it on the left side. I'll bring over all of this dy dx terms to the right side. Meanwhile, I'll go ahead and factor. So this dy dx is really just one of them. I bring this to the right side by subtraction. And I bring this to the right side by addition. And so I took care of 2 steps. And when I brought these 2 terms to the right side, and then I factored out the dy dx. So then dy dx is just isolated. It's going to be the sine y in the numerator, this whole long expression in the denominator. And that would be your final answer for that derivative. Okay. So yeah, that's the general proper process for implicit. And again, just be careful, follow the usual rules. Every time you take the derivative of the y, something with a y in it, you've got to follow it with dy dx as for the chain. Let's look at this guy right here. This is y equals rad 6 plus 7x over e to the 5x. Now the question is, now that you've seen a couple different ways, do we use quotient rule, or do you want to use ln properties? So this addresses an earlier question. Frankly, both work. So the answer to both would be yes. Okay. So really, it's a question of how much work are you willing to do. If I do the quotient rule, this one's not too bad. I can probably get away with the quotient rule. It's going to look ugly, but I can probably get away with it. Let's do it. It's going to be bottom times derivative top let's see, then I have a chain rule that's going to turn this into a 7. Ah, 7 right there. Minus the top times derivative of the bottom, which is 5 e to the 5x. All over the bottom squared, which would be e to the 10x. That's the quotient rule. Now, this is correct, but it is messy. It is ugly. So let's try it with the ln properties. So I would take ln both sides. Ln y equals ln of all this loveliness. I would split apart the right side. I'm going to do this I'm going to take care of a couple of properties in one fell swoop. And I'll kind of verbally talk what I just did here. I broke apart the quotient as a subtraction. This radical is actually the 1/2 power, so I brought it down in front. ln of e to the 5x, ln and e cancel, you just get negative. Well, you just get 5x, but the minus sign then attaches. So we take the derivative of both sides using the implicit form. So we do, okay, so we just again pop the 6 plus 7x in the denominator, put its derivative in the numerator. 1/2 is just sitting up front, enjoying the view. And then the derivative of negative 5x is negative 5. And then finally, we just kind of clean it up. So I'm going to copy all this. I leave some space here for the original function. The original function is this guy right here. And that's done. Now I ask you, these are 2 answers. They're actually the same. Do they look the same to you? Does it jump out at you as being identically the same thing? Probably not. But they are the same. So I like ln method because again, you're doing a lot of simplification in the initial break apart with the logarithms, so that when you take the derivative, there's really very little simplification necessary other than just little cosmetic things.
This is kind of a silly question, but how confident are you that both those answers are to be accepted by the website?
Oh, if they're equivalent, they'll be accepted.
Okay.
It
Because I
uses
had
a-
done some other ones, like I did number 50 with LN initially, and then it was so different than your answer, which wasn't done that way. I was like, I couldn't tell if I was wrong or right because it is so different.
it uses a method it basically graphs them. So somewhere in its eternal memory, it basically just runs through a comparing graphs, and if the graphs are the same, it's considered the same.
That makes sense. Okay.
So yeah, it's actually kind of a low. I would say it's like an old 1990s era routine that kind of checks that they're the same. It's a pretty it'll be accepted as long as you first of all get it right, and second of all are enter it syntactically correct. That's the big key. You want to make sure that you don't miss a parenthesis, that you've got everything exactly how it should look. All right. Okay. Let's just kind of run through these. The first few are just a bunch of power rules. I'll give you some hints on these. Like for instance, on this number 4 here, you wouldn't really want to use the product rule because you can FOIL this first, and then it's just power rule. Same with number 5. Number 9, for example, I wouldn't use the quotient rule because actually, if you factor, the x plus 2's cancel. Same for number 10. You can actually pull out or treat the t squared as a denominator for each of these guys individually and turn these into just a bunch of power rules. So you have these properties at your disposal, but you also have to know what's the best property to use at any given time. If, for example, let's say on number 9, you did the quotient property on it and you were careful and you did everything correct, you would get the correct answer. But what I'm trying to emphasize here is that this problem here would, if you factor and cancel first and then take the derivative, you're done like in 3 steps. If you do it the lengthy way, you're going to be doing it for like 10 or 12 steps. So a lot of what you're learning here is also tactics. What's the best method to use? And that just takes practice. For number 11, you got some weird exponents. Okay, you can probably do that. And now, okay, without a calculator, all right, just bring the 0.7 down. Just type it in as 0.7 times 0.27 t to the, and then you take away 0.7. You can probably do that. That's going to be negative 0.3. And then same for here. I would bring the 0.15 down. Negative 0.15 times 3.42 t, and then what's that? Negative 0.85. So the arithmetic is not too hard. Number 12 and 13, you have chain rule. And again, interrupt me. If you want to see one of these worked out, I'll do it.
I imagine on number 11, like number 11, if we really don't want to do the math, the 0.15 times 3.42, we can use Desmos. Desmos be available?
No, there's no outside help on this one.
Okay.
So if you were to get this one on the test and you don't want to mess around trying to work it out by hand, you don't have to. Just bring the 0.15 down in front, and it would be negative 0.15, so parentheses, negative 0.15 times 0.342. I'm sorry, 3.42. So you can actually just write it out in its lengthier expression form. That would be fine.
Gotcha. Thanks.
It actually takes a lot of the pressure off.
Yeah, you won't be having any outside assistance on this one. Make sure you know your sine, cosine, and tan forms. A lot of people get the minus sign messed up. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tan is I'm sorry, I didn't say negative. Derivative of tan is secant squared, and then of course x, and then of course any chain rules that apply. Number 24, again, don't use the product rule here if you don't have to. Distribute the 6 rad x through and just treat these as fractional powers. It's easier. Okay. I put cotan, secant, and cosecant here. I put them down because just almost like we're kind of acknowledging they exist. But in each of these cases, you can actually turn these back into sines and cosines using quotients. And you get clean, you know, you can just do them that way. And again, teaching, as I teach this later stuff, if you might have your Calc 3 maybe in a couple semesters, I can count on like one hand how many times we play with cotan and cosecant. We just don't. Now secant pops up a few times, but even then we can kind of dance around it. We almost never, ever, ever play with cotan, cosecant. All right, like number 29, I give you a hint. Don't use a product rule. If you use trig identities, this thing actually reduces just a sign. Okay. We ran through a couple of these later ones, like number 30, well, okay, 34, bring the 2 down in front, 2 sine 6x, and then derivative of sine 6x would be cosine 6x, and then an extra 6 because of the chain rule. Whoops, didn't need to do that. Hey, we're gonna skip so over like that. You have a few, like right here where you have, oops, why does it do that? A couple here where you have to use implicit forms. We just did one of those. And so really these questions that I pose here are really representative of what you're going to see on the mastery. Again, the mastery questions are taken from your homework, every single one. So you have seen them before. And then really in a few cases, I'm just trying to give you a little hint, you know? And so we worked out a few of these, like number 63 we did earlier. And you know, we were able to work out 63 in like 5 lines, whereas if we tried it without logarithms, we'd probably still be working it out. Funny enough. All right, so it is 6:50. And what I want to do, yeah, somebody asked, can you just write t to the negative t to the parentheses 0.7 minus 1? Yes, you can. I'm actually going to power down here because I'm going to post this on my YouTube channel. And I'll send a link out. It'll probably take about a half hour for everything to work out. But the mastery actually starts here in about 9 minutes. So I'm going to basically glue myself because I'm always afraid that there's something wrong with the setup. So I want to thank you all for attending tonight. We had 23 participants, and I really hope you guys do really well. So thank you. And you guys have fun on the mastery. I'll see you, I guess, in a couple days when we do test 3, right? Bye.